Welcome to the first lecture of Unit 3, Forces Within. Unit 3 focuses on processes that exist or are driven by the dynamics and the mechanisms that are at work in the interior of the solid Earth, but that have manifestations on the surface. So Unit 3 we'll get to in later parts of Unit 3, earthquakes, volcanoes, large-scale structural crustal deformation, mountain building, things like that. However, Unit 3 begins with a discussion of the driving force of all of those processes, plate tectonics. Plate tectonics is covered in Chapter 7, and this lecture will be a little bit different than previous ones in that it will be entirely graphically based. So grab your book, follow along. There won't be as many words on the screen, but hopefully that'll be a good thing, and we'll go through many more graphics than we normally do in a lecture, but I hope that the time will be the same. So plate tectonic theory arose in, well, the beginnings of plate tectonic theory arose in the early 1900s with several scientists, but the most notable of whom was Alfred Wegener, a German geologist, who, due to his observations about the arrangement of the continents, the shape of the continents, as well as fossil evidence and other geologic evidence, proposed what he called his theory of continental drift. That is, he proposed that continents over long periods of geologic time would actually drift around the surface of the globe, plowing through the ocean crust or be organized in various different arrangements. The fundamental basis for that theory of continental drift was his observation that many continents actually appear to fit together like puzzle pieces. Now, when you look at a globe, you see that. Most people do see how South America could fit right into Africa, for example, or that North America, if you curve it and twist it, it will nuzzle right into the northern part of the African continent, as well as in Europe. However, what's even more striking is that if you factor in the continental shelf, that is the true boundary of the continental crust or the ocean crust, those fits become even more impressive. You can see here there's very little overlap in the continental shelf of South Africa of Africa fitting into the continental shelf of South America. Wegener also observed or noted that fossil evidence supported his theory that continents at one point were clustered together. Mesosaurus existing both, or fossils of Mesosaurus existing in the African continent as well as South American continents, could have theoretically evolved. I'm using theoretically in the general sense there. Could have, I should say hypothetically, evolved separately but exactly the same way on two different land masses separated by a vast distance of water. However, a more reasonable, simpler explanation is that they are representatives. The fossils that you find in South America versus Africa are actually representative of the same community of organisms that were at one point in contact. In fact, it was just one ecosystem that eventually got separated by geologic processes. The same can be said for Lystrosaurus and Glossopteris fauna or flora. Those exist or are found in the fossil record across a wide range of continents that are in the present day separated by large expanses of water, making it unlikely or a less reasonable explanation that they evolved separately but exactly the same in these locations. The simpler explanation is that they actually are just representatives of the same group of organisms that evolved and were eventually split and separated by movement of the continents. Other evidence that Wegener cited for his theory of continental drift were that mountain ranges are geologically identical on both sides of large ocean basins. The best case for that is, or the best example of that is the Appalachian Mountains in the eastern mid-Atlantic and northeastern United States, up into the Canadian Maritimes. The actual exact same rocks and patterns of stratification and evidence for structural processes occur or are shown in mountain ranges in the British Isles as well as the Caledonians and Scandinavia. The explanation is that at one point when North America was much closer to Africa and Europe, those mountain ranges in this boundary were built and were only separated by geologic processes over hundreds of millions of years. And lastly, the fourth linchpin, or the fourth piece of compelling evidence that Wegener cited, was the presence of glacially striated or glacially eroded rock on many of the continents in the southern hemisphere, that is South America, Africa, Australia, and India, as well as on the Antarctic continent. Evidence for glacial erosion often is based on the presence of tills or stratified drifts. We learned about those in what chapter was it? I'll look at my book quickly. That was chapter 6, the last chapter. Presence of moraines near glacial terminations also is evidence for glaciation. However, one other sign of glaciation, and we learned about this in chapter 6, is the presence of glacial striations on bedrock. That is, as glaciers, large, huge, thick, miles thick masses of ice moving across bedrock with large quantity of a large mass of boulders all the way down to silt, dragging along or entrained in its lower sections, actually cause erosion and can scrape away layers of soil, unlithified material, and can actually cause scratches in bedrock, in hard bedrock. This photograph is an example of glacial striations. You see, moving from kind of the left side of the screen to the right, this pattern of long linear lines. Those are not known to be caused by anything such as water or stream flow erosion. They're not caused by wind, or they're not due to mineralogical differences. They're literally scours from large boulders and rocks that are dragged along the bottom of glaciers during glacial periods. So the presence of glacial striations in a large number of continents, South America, Africa, India, and Australia, as well as other glacial features like moraines that are dated to the same time period, all associated with Antarctica, led Wegener to conclude that at one point those continents were all clustered around Antarctica in the southern hemisphere, probably at 60 degrees south latitude, in kind of the polar regions where an ice sheet would expand and cover a much more vast area. So those four lines of evidence were pretty compelling to argue that, in fact, in the past, the continents were arranged differently than they are now. However, what was missing was a cohesive explanation of why, like what would cause that to occur. Scientists accepted that it did occur, or that it could occur, and the evidence suggested that it did. However, nobody could think of a reason why it would occur. There's no physical mechanism that would support the idea that continents were plowing their way, like ships in the sea that were plowing their way through continental or oceanic crust, moving around the globe. That is until Earth scientists started to observe and note and measure and map what are now known as the boundaries between plates, or as tectonic plate boundaries. In particular, in the middle of the oceans, there are features called mid-Atlantic ridges. These are topographically high relative to the abyssal plains, which are very low and flat. Topographically high, that is, they stick up from the seafloor, essentially mountain ranges under the ocean, or at the bottom of the ocean. These weren't really observed or recorded until the 1940s, 1950s, during in a period when nations, especially large world powers, were engaged in conflict, either direct or proxy, in the world's in various theaters around the world. There's a lot of submarine traffic. The Soviet Union and the United States, and eventually China and other countries, joined in and tried to place and move their strategic assets around the globe using ships and submarines, and it was in their interest to know exactly what was the structure and morphology of the seafloor. Well, what was discovered was, well, I should step one back. One of the best ways of determining the structure and morphology of the seafloor was to pay scientists to map it, to study it, and that's what happened in the 40s and 50s and 60s. Is the heyday of seafloor mapping and ocean marine geology, where lots of new discoveries about the oceans were made. One of those was that there the presence of these ridges that prove that exist around the globe and through the oceans, through the Pacific Ocean, Antarctic, Pacific plates. There's lots of interesting seafloor and subsurface features down there that weren't known beforehand and weren't known to Alfred Wegener. The discovery of these features led eventually to the integration of Wegener's continental drift hypothesis with the modern plate tectonic theory. There are several plates distributed, or many plates, in fact, distributed around the globe. Most are, or many are large. Some are medium, and there's a few tiny ones around there. Cocos Plate is a pretty tiny one. The Scotia Plate, small. There are the Juan de Fuca is a real tiny one. But they can cover vast areas of the global surface. The Pacific Plate is the largest plate there is. Plates interact with each other, both near field and far, meaning that when plates are rubbing up and in a direct contact with other plates, those forces can be pretty intense from a geologic perspective. They can crash into each other, which is plates are converging. They're moving toward each other. That's called a convergent boundary. When plates are moving away from each other, that's typically called a divergent boundary, right here. And the other kind of plate relationship is called a transform boundary. That's where plates are sliding past one another. Plates can also impact other plates from a far field perspective too. That is, they don't necessarily need to be touching or adjacent to have impacts. And that will be discussed a little bit later, but in a nutshell, plates that are moving on one side of the globe by indirect effects can cause motions in other plates, which then produce motions or affect the motion of plates that are not actually touching. So the plate tectonic system is an incredibly complex. It's a three-dimensional system. Oftentimes we view it, especially in cases of this map, on a two-dimensional surface, but there's a lot of three-dimensionality to the motion and to the structure. Divergent plate boundaries are where crust is moving away. A new crust is being formed and plates are moving away from one another. These occurred on mid-Atlantic or mid-ocean ridges. Remember, the mid-ocean ridges were one of the first seafloor features discovered in the early days of plate tectonic research. Mid-Atlantic or mid-ocean ridges are topographically high relative to their abyssal plains adjacent to them, and then eventually get to the continental slopes and shelves. Mid-ocean ridges or divergent boundaries are caused or characterized, by upwelling or the rising of hot magma from the mantle on the asthenosphere. That magma, when it reaches the surface, cools and forms brand new crust. In order for new crust to form, old crust has to move out of the way, and it does this by the rising of the new magma drives these plates apart, drives them away from each other at the mid-ocean ridge. Crust on either side tends to match up with crust on the other side in certain distances away. So the crust that's moving away from this mid-ocean ridge here and the crust that's moving away from here, crust on either edge over here and here, is probably the same age, formed at the same exact time in the middle of the ridge. And that comes into play, or was used by geologists to actually determine what actually happens at mid-ocean ridges. They were able to use dating techniques to measure the age of the crust on either side, and were able to therefore conclude, well, wow, this crust on one side matches the age on of the crust on the other side at the exact same distance. That must mean that this crust, both of these places, were formed at the exact same time and probably the exact same place. What could explain that? Well, the notion of a divergent boundary arose based on that observation. Divergent boundaries occur across the globe. The Antarctic and Australian Indian plate is a big one. The one that most folks know and think about on the East Coast is the Mid-Atlantic Ridge, which goes from the northern Atlantic all the way through Iceland, all the way down to the Southern Ocean, and where it joins up in a triple junction with the Antarctic plate. The general progression of divergent boundaries, or the general path that those follow, or the events that occur when crust rifts and splits and diverges or spreads apart, is that usually in a continent, a zone of mantle upwelling is occurring where there's a lot of heat, and that causes the crust to flex or to distort. And you can see here that the crust is kind of bending and warping due to that heat underneath. Mantle material can protrude up as the crust flexes and faults. Crustal blocks will drop relative to other crustal blocks, and you'll form very characteristic geologic features of crustal block faulting. As that upwelling continues, crust on either side of the rift or the divergent boundary starts to spread outward or migrate laterally away from the center. Eventually, it can move so far away that a linear sea or ocean water can infiltrate in and create kind of a long, thin sea along that crust along that crustal flexure, or that point of divergence. Ocean or basaltic crust starts to form due to the upwelling of mantle material, and eventually you get to this ocean stage over hundreds of millions of years, where you see a well-defined mid-Atlantic ridge, a long, deep ocean basin on either side, eventually leading to the continental rises. Let's get back to where we were. Sorry about that. East African Rift is a rift that most geologists learn about early in their careers. Rifting doesn't necessarily occur on a single line. It actually occurs in a pattern called a triple junction, or a triple rift. And that's because the Earth is a three-dimensional shape, and to split apart the skin of that shape, or the Earth's crust, it doesn't actually split in a line. You have to split it three ways, roughly 120 degrees between each split, in order for the geometry to work. But here's a real-world case of a rift valley. The Red Sea splitting apart, you have a nice linear seaway in there. The Gulf of Aden is another arm of that rift. It's an inactive rift, failed. And then the active rift in the African Rift Valley, protruding all the way down through Lake Victoria and Lake Tanganyika and Nyasa, are eventually going to open up, and over probably 200 to 300 million years will form a vast ocean. The Rift Valley in the real world looks like this. You can see these fault block, crustal fault blocks structure that due to the rifting, large blocks of Earth's crust, 5, 10, 15, 20 kilometers across, will move relative to one another. Convergent plate boundaries are the second major type of boundary, and those occur where plates are moving toward each other. So divergent plates are moving apart, convergent plates are moving toward each other. Well, you can imagine when two large plates will move toward each other and they hit, something's got to give. Either they'll crumple and move up into that space up in the atmosphere that is free to accept new material. They don't typically crumple and move down, but occasionally, not occasionally, often, one of those plates will do something called subduct beneath the other. That is, it will dive down underneath it, back down into the mantle. And that's usually controlled by density differences. So basaltic crust or oceanic crust is much denser if you had than granitic or continental crust. If you had the same size, the same volume of granite and basalt, say a baseball-sized mass of granite and basalt, the basalt mass would be heavier, would weigh more, would have more mass than the granite. So that's because it's denser. You can think of it in simple terms as the granitic crust is lighter and the basaltic crust is heavier, but technically speaking, it's density that makes the difference. Now, denser things will naturally tend to move downward relative to less dense things due to gravity. And that's what happens in the case of continental oceanic collision. Continental crust, characterized by granitic and less dense material, will right on top of a subducting basaltic oceanic crust. Looks a lot like this. So here we have an example where the oceanic crust, which is denser basalt, colliding with a thick but less dense continental crust. That oceanic crust will dive down. Usually drags a lot of seafloor sediment, including water. And water actually lowers the melting point of a lot of these minerals. And so you get partial melting and full melting deep down in the kind of 150, 200 kilometers of depth. And that molten magma will rise to the surface through continental lithosphere and create volcanoes. Oftentimes, these Andean-type volcanoes are usually with andesite as the dominant mineralogy, will occur at continental ocean arcs or subduction arcs, as they do all along the western margin of South America and the western margin of North America and the eastern margin of many Asian or Asian continent or Asian locations. Sometimes oceanic plates collide with other oceanic plates, and you can still get subduction, even though both oceanic lithospheric plates tend to be similar in density. One other difference that can make one plate subduct beneath another in terms of density, and that is older plates or areas of crust that are older are generally are cooler than plates that are a little fresher, or sections of crust that are fresher, that are more recently generated at a mid-ocean ridge. So if one particular oceanic plate is more dense than another, then subduction will occur. And you get the same process of subduction in training water and other seafloor sediments, lowering the melting point of many of those minerals, and you get more volcanism, but in this time it's called island arc volcanism. It's essentially the same process as happens with continental volcanism, but the mineralogy is slightly different, and the way it looks on a map is a little bit different as well. You'll find strings of volcanoes out in the middle of the ocean, not to be confused with hotspots or seamounts, but you'll find arc-shaped strings of volcanoes at plate boundaries out in the middle of the ocean. And then continental collision is different again. Continental collision, you oftentimes do get subduction still, but what you also get is lots and lots of mountain building. Well, probably the most famous example is India colliding into the Asian continent. You know, over 70 million years, India was way out in the Indian Ocean and has migrated enough to collide with the Asian continent, and oceanic plate subducts until continents hit each other. Neither is subducting because they're both about the same density, and instead of major subduction like it would happen, or like would happen in an oceanic continental plate collision, you get some subduction, but what you get a lot of is scraping up of material and mountain building. The Himalayas are probably the most famous example of continental mountain building. Shows India migrating, the distance it travels over millions of years, and pictures of the height and dramatic nature of continental generated mountains. Transform boundaries are the third major type of tectonic boundary, and those are caused caused or generated due to the need for plate motions to accommodate the other plate motions as they occur on the Earth's surface. So when you have a lot of convergence and subduction, there's going to be some necessarily stress on some plates moving in the lateral or transform direction. That is to accommodate the three-dimensionality, the curved surface of the Earth. When you're moving plates toward each other and against each other, things slip and slide on the edges, and you get typically very, very striking strike-slip faulting, plates moving relative to each other in a lateral direction, not crashing into each other, not splitting apart. So here's a mid-ocean ridge where crust is moving outward on either side, but in a different place that mid-ocean ridge might be slightly offset, and so you get crust moving side to side, and you have crust moving in opposite directions in this case, and that's a that's a transform fault. They occur in other locations. They can occur at subduction and at divergent boundaries, but they're very characteristic of earthquake activity. The Juan de Fuca plate, as it is being diverging relative to the Pacific plate and is subducting relative to the North American plate, is a zone of high intensity seismicity. It's connected to the San Andreas fault. Those are all transform boundaries. This is a picture, a really interesting picture of a transform fault at the San Andreas fault. This river valley was at one time connected with that river valley. Transform faulting has moved those two bodies, two masses or those two plates laterally relative to each other. An interesting aspect of seafloor spreading or divergent boundaries is that sediments increase in thickness the further one goes away from the mid-ocean ridge. Remember, at the mid-ocean ridge, or at any mid-ocean ridge, the crust at the very, very center of it, at the ridge, is youngest. It's brand new crust, and it hasn't existed for very long. Therefore, the amount of sediment that it can filter down through the water column or make its way off the continents and fall to the seafloor and accumulate is very, very little. So sediment thickness is very little at the center of the ridges. However, as you move away from the ridges, sediment has more time to accumulate, the oldest material being the furthest away from the ridge at any given time. So those are where you have the most time for sediment accumulation, and drill ships, or scientific drill ships that collect sediment cores to look at earth processes over long periods of time, will often go to these regions where sediment is very, very, very thick, and the age of these sediments at the very bottom are very, very, very old. Sediments at the surface are, of course, brand new. This is a photograph and schematic of a typical drill ship. This is, if I can tell, can't tell which one it is, but it may be what's called the Joides Resolution, or there's a Japanese drilling ship called the Rikyu. Anyway, these ships are really interesting scientific machines. They cost a lot of money to run, but the data they've retrieved is quite amazing and important for our scientists the world over. These ships will hover over a certain spot and can drop a drill pipe down several kilometers to the seafloor, and then can continue to drill and extract in relatively unaltered form sediment layers from the seafloor. What's really cool about these ships is they can leave a cone and they can come back later and go back down in when they bring more drill pipe, or if they need to come back to redo things. They're pretty amazing. A fourth feature of the large-scale global tectonic system that's not a boundary per se, like divergent, convergent, or transform boundaries, are hotspots. They often they reflect plate motion quite dramatically. And what those are areas of mantle upwelling and volcanism in the middle of plates. They do not occur on the edges of plates. The Hawaiian Islands, which is more properly known as the Hawaiian Emperor Seamount Chain, is a series of volcanic islands and seamounts. Seamounts are basically volcanic islands that don't protrude out from the surface of the water. The Hawaiian Emperor Chain is a series of seamounts in the Pacific Ocean, in the middle of the Pacific Ocean, that are caused by mantle upwelling, volcanism, and plate motion. Let's explain that. Here's what it looks like. The Hawaiian Islands are here. This is where most people go to vacation, but there's a long string of islands that go off there. And then the Emperor Seamounts are up here. What's interesting here is that about 43 million years, the seamount here is 27 million years old. The Sukyo is 65 million years old. These are brand new. These are the youngest crust. We've got about 40 million years old around here. This bend actually indicates that plate direction changed at about 40 to 43 million years, in the past. The way a hotspot forms, or a volcanic hotspot island or seamount, is that as a plate is moving, which they naturally do and they always do, you can have rising heat mantle plumes that migrate toward the Earth's surface and will generate volcanoes. But as a plate continues to move relative to the stationary mantle plume, what you get is a repeated source of repeating islands. So you have magma moving up, coming through the surface, a volcano forming. It may break the surface, may not, of the water. It may be an island. It may just be a seamount. But over time, that magma may settle back down and not go for a while, but it starts to collect some more and more and more. But all the time, this plate is moving across. By the time this mantle upwells again and creates another volcanic seamount or island, that plate is moved, and that old one is now over here, and a brand new one forms. The plate's continuously moving, forming basically a chain or a conveyor belt of volcanoes. So let's go back here. So if we're looking at this graphic, we can see the hotspot is basically right here. 65 million years ago, this island was back here at the hotspot, and over time, it was moving this way. And then about 43 million years, the plate motion changed, and the plate started to move this way. Actually, sorry, I did that wrong. This was here at one point. 40 million years to there. 65 million years to there. That's the path it followed. Now, one of the other interesting things about the solid Earth and the mantle and the solid and liquid inner and outer core is that they generate what's called the dynamo, and that gives the Earth a polarity or magnetic north and south. Rocks that contain iron and other magnetic minerals, when they're formed at a mid-Atlantic or a mid-ocean ridge, when they're formed from magma, they're solidified, the actual mineral grains take on, let's skip ahead, the mineral grains take on the polarity. They record the direction of magnetic north, or they record the orientation of the Earth's magnetic field when they solidify, when they cool. Now, over long periods of time, the Earth's polarity scale has switched back and forth from normal to what's called reverse polarity, and you get small little reversals. It happens on scales of 500, 700, 800 million years, 800,000 years to a million years. Sometimes these reversals or these periods last several million years. But basically, the compass direction on the poles on the Earth flips back and forth. And what's interesting is that compass direction can be recorded in rocks. And so as these new rocks are migrating outward from a mid-ocean ridge, they're recording the dominant polarity of that period of time in which they were formed. And as they progressively form and you get more and more rocks, they will record the polarity as it switches. So in this particular example, the white rocks that are forming right here are recording a normal polarity zone, a region of normal polarity. That is, magnetic north is where magnetic north is today. Over time, there may be a polarity reversal, and rocks that are forming newly at the mid-ocean ridge are recording a reverse polarity. And it may then eventually switch back over a couple million years, and they might record normal polarity again. But what's interesting about this is that if the ridge is right down the middle, that the pattern of magnetic polarity striping on either side is exactly the same from one side to the other. That actually gives further evidence to plate tectonic theory, or at least it supports the notion of divergent boundaries. This is real world data along the axis of the Juan de Fuca Ridge, where the divergence is taking place, and red and white is basically periods of reversals and non-reversals. It's a complex region in this northern Pacific region of the Juan de Fuca and Pacific Plate. There's lots of complex transform faults, but the general pattern of striping is similar if you look real close. This is another way of looking at it and seeing the magnetic striping, and you'd get magnetic or ships that tow magnetometers across ridges will get this magnetic data that looks basically a series of the strength of the magnetic field of those rocks. And you can see the pattern. If you look from the center outward, the pattern of peaks and valleys is identical, is a mirror image of what it is on the other side, which means that that these two these two sides started off in the same place. That is, when rocks at this magnetic point formed, they formed in the mid-Atlantic ridge right when the rocks of this magnetic point formed, and they spread outward. When rocks over here in this kind of triple set of peaks were forming, they were back at the ridge along with this set of rocks with this triple set of peaks. You can see the striping up here in that cross-sectional view too. It matches on one side with the other. Now, what will happen in the future? The same thing that happens in the past. Continents move around over long periods of time. You can see Pangaea at 200 million years ago. Continents started to rift, continents started to split. You can see the rifting of North America from Africa at 150, 80 million to 50 to 20 to the present day. It takes a long time for continents to rearrange themselves, but you can imagine how interesting that is for geologists to study, but how important that would be for things such as evolution and climate change, would depend heavily on ocean circulation and where continents are located relative to ocean moisture. Plates move very slowly. These arrows indicate are relative to, or give an indication of the velocity of plate motion. You can see that not all plates move at exactly the same rate, nor do every location within a plate move at exactly the same rate. North American plate, all moving from the Mid-Atlantic ridge, 2.3, about 2 to 2.5 centimeters per year. But look at these Pacific plate motions. These are ginormous arrows. They're moving at 10 to 15 centimeters per year. Textbooks oftentimes will indicate that plates move at 2 to 2.5, or that subduction zones move at 10 centimeters per year. It's too simplified in a way. Plates move at different rates, but in general they move very, very slow from a human perspective. So what drives the plate tectonic system? Well, it's convection. It's basically the basic principle that things that are warm tend to be less dense and things that are cool tend to be more dense. And less dense things tend to rise relative to cool or less dense relative to more dense things. Less dense things rise relative to more dense things. So when you're boiling a pot of water, the water on the bottom will get hot and will tend to rise up toward the surface. Cooler water replaces it. The same thing happens in oceans today. It doesn't have to be boiling. It can only be a degree difference in things, and that same thing will happen. But it also happens in semi-fluid mediums such as hot molten magma in the Earth's interior. This graphic is our standard continental oceanic subduction zone picture, but what it does include here is mantle material. It shows the convection cell that is driving mantle up, causing spreading at the mid-ocean ridge, moving over where you get subduction. So it's the same as driving up in the center, moving laterally away, sinking back down. So it's a big loop. So the Earth is characterized, the interior of the Earth, the asthenosphere, is characterized by a lot of these big loops of heat, hot material moving up, material moving out where it cools, and when it gets cold enough to sink, it sinks and circles back around. Cool enough to sink, it sinks, and as it gets more toward the interior of the Earth, it warms up again. This is a bigger picture of the convection cells that people, or that earth scientists hypothesize exist in the interior of the solid Earth. You notice this boundary of where subduction tends to stop. Many scientists think that this stops at about 660 kilometers, that you don't get convection below it. Other scientists think you do get convection below it. And in fact, it can explain somewhat the difference in mineralogy or lithology of ridges versus island arcs versus island arcs over here versus hot spots over here. That hot spots tend to grab mantle material from deep in the mantle and come up, and that lithology or chemistry can be quite variable. Whereas upper mantle, which is well mixed and well kind of stirred up, tends to be mid-ocean ridge generated basalt, tends to be pretty uniform the world over. But you can see the large-scale structures of ridge and lateral movement of crust to crust, and then subduction back down. Now, what's one interesting thing is that many people tend to think that the driving force of tectonics is the mantle upwelling, that is the asthenosphere upwelling, the heat rise that causes new crust to form and has to push it out sideways in order to make room for more. Well, there's some recent papers have been published in the last year or so that lend a little bit more that suggest that, well, actually the subduction zones have a lot more influence than we once thought. And it's indicated here by slab pull at trench that the slab dropping down with density is actually pulling material apart over here at the ridge, sometimes thousands of kilometers away. Whole mantle convection is another model for internal Earth or the driving force of plate tectonics, and that shows that subduction actually occurs much deeper beyond the 660 kilometer boundary. There's some evidence that suggests that, and again, most of the evidence doesn't support this as much as the 660 kilometer boundary model, but you still have hot spots. It can explain all of the occurrences: mid-ocean ridges, hot spots, mega plumes, regular plumes, subduction driving these things down. This is all inferential models. Nobody has made actual observations of what is happening down there in the mantle, and hopefully by this point in the course you can imagine why. This is just closing this lecture out. This is a picture of the continents now, showing many of the plate boundaries, subduction boundaries, right here, typical transform and spreading centers there. Over time, 200, 300 million years, as these plates follow the directions that their arrows are indicating, they're moving. North America is moving to the left or to the west. Europe and Eurasia that way. This is one potential rearrangement or reconvergence of the continents. You'll notice that in Pangaea, Antarctica was tucked up in here. In this particular plate configuration, right now it's not. Africa and North America are rearranged a little bit differently than they were in Pangaea, but the general gist is that plates will follow some degree of cyclicity and will oftentimes have similar relationships over long periods of time, geologic time. Just a closing slide to again remind you that plate motions are, for the most part, similar but not identical. It can range from 2 centimeters per year to upwards of at some really fast subduction zones, 15 centimeters per year. So I hope this graphical lecture was a little bit better than the earlier kind of more word-based or text-based lectures. We'll see you next in chapter 8. Thank you.